Okay. Um, Quantum stuff that I don't agree with, or that I find um, flawed. Uh, yeah. So, um, scale. So the measure thing. Um, the quantum gibberish usually states um, everything. Um, I say it, that like a particle doesn't actually exist in any one location until it's measured and stuff like that. Um, but their form of what they call measuring isn't the only. I say it's not necessarily the measuring that's doing the problem. It's the way they're measuring. So you spin a coin on a table, you spin a quarter on a table, and it's spinning. Is it heads up or heads down? It's not really either. The coin is actually horizontal, so if anything, it's heads forwards or heads back, but it's also not really either of those unless you are looking at a specific um, short time interval. If you look at a time interval that is longer of a certain of any of much duration at all, the coin has already spun around several times, and it's both heads up and heads forward and heads back. So that's not really a good way of. So like your form of measuring is flawed. Um, it'd be like saying um, the whole apples and oranges things. It'd be like saying um, how many pounds is a second, or how much uh, how many rocks for Mickey Mouse, or something. It doesn't compute, doesn't make sense. Um, so what they do is they take the spinning quarter, um, and then to make it be heads up or heads down, they drop an anvil on it and smash it and look at it and say, "Oh, it's heads up." And then they look, and then they smash another one, and they smash it, and it's like, "Oh, this one's heads down." And they say, "Oh, like this proves that something weird is going on." And the weird thing isn't that. The weird thing is that they're smashing things and calling it measuring. Like if a preschooler went in and said, "Are you red or?" I'm trying to think. So if a preschooler went around with a hammer and started classifying things as colors, and then you're like, okay, like he goes up to a watermelon and is like, is this red or green or purple? And he takes the hammer and he smashes the watermelon. He's like, oh, look, it's red on the inside. It's red. And then he goes up to a cucumber. He's like, well, what color are you on the inside? It's like, oh, you're like a light green. And then he goes up to a acorn. It's like, oh, you're light brown. And he goes up to a person and he starts smashing their foot. And he says, oh, look, you're red too, just like a watermelon. You two must be very similar. And nobody seems, and then like so that's flawed in itself. But then the other thing is saying that nobody seems to say like, oh well, like like nobody seems to even raise an eyebrow at the whole like smashing someone's foot with a hammer to see what's inside. Yeah. What else? Okay, so there's that. It's not exactly that bad, but and so there are a few phenomena that are interesting in the fact that you so like the whole like quantum teleportation thing and all that stuff, but like I mean first of all that's super fuzzy and then okay this brings up more stuff. There's tons of ways that things could be misunderstood. Um, so Next one, quantum teleportation. So we went over the whole measuring and two places at once thing and all that stuff. So measuring. No. So measuring quantum teleportation uh, is how do you say it? To my understanding, quantum teleportation states that every particle, that what we call particles, are really um, possibilities or probabilities, and that there's a possibility of a particle existing here or there or anywhere type thing, and that there's like a probability function of, so like if you have a basketball, there's a probability of the basketball um, like moving in this curve or this bend or this arc, and there's also a probability of this of the basketball existing in this space or this space or this space or this space and stuff like that. Um, but and so like if you throw a basketball at a wall, most people would say yeah it'll bounce off the wall, or if the wall's like really weak or something, then it might dent the wall or something like that. Um, but in order to get through the wall, you have to break the wall, right? Quantum teleportation states that there's a slim chance, ever so slight, that the basketball can, um, like, win the lottery and exist on one side of the wall and then instantly exist on the other side of the wall. And the way that they say that they prove this is they take electrons and they shoot them at something, um, and then they have a little measuring thing on the other side of the obstacle. So they have like a little wall, and they're shooting electrons at it. Um, and as they're shooting electrons, they're counting the electrons on the other side or something like that. I can't remember exactly how it goes, but the way they state it is that electrons like take a certain amount of time to get through, or electrons don't get through, or things like that. Either way, um, they say that some electrons seem to get there faster. So like you send one electron, and then you send another electron. One electron goes forward and hits the wall, and takes a while to get through it and get to the other side. And another electron you shoot, and um, oh, it seems to like jump forward and get there before the first electron, and things like that. I probably have several things wrong with that statement, but first of all, um, I want to say that something I do that I might be wrong, but I want to say is correct is I want to say that in order to observe this phenomenon, you have to be shooting tons of electrons. Um, Maybe not tons compared to like what the electricity in like your wall plug or something like that, but tons of electrons. Like if, as far as like counting every single one of them, it's like billions or trillions or more. Um, so you have to have lots and lots of electrons going. So first of all, how are you differentiating and counting and stuff like that? So like you've got if you've got anything anytime you're dealing with large numbers, like you got to be really careful about the counting methods and stuff. Then moving on to some other stuff. Um, there's so kind of along with the accounting method. Um, first of all, okay. So first of all, a basketball and a wall comparatively look pretty solid. Um, um, that if you were to throw a basketball at a wall with holes in it that are hundreds of times bigger than a basketball, so like I'm trying to think. Yeah, I mean like if you were to throw a basketball at a wall with holes, like there was like almost like Swiss cheese that had holes that were like hundreds of times the size of the basketball. So the basketball is like say like a foot wide, and you've got holes that are like miles wide in this Swiss cheese block. and you're throwing the basketball at it, um, it's conceivable that the basketball could get through, first of all, and that your numbers, based on like a just a rough estimate of like, well, like on average, a basketball thrown at this wall will take this much time to get through, because it has to bounce and things like that. But that like there could be some massive outliers out there. First of all, the first time the basketball bounces or interacts with anything, you're gonna have a massive disruption. Now electrons are different and things like that, but yeah. But so the basketball being thrown at the wall, um, you 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 don't see holes everywhere. With an electron, the electron is super dinky, and when you're throwing it at anything, every piece of matter, unless it's a neutron star, is like throwing it at a Swiss cheese block with holes miles wide, type thing. Um, so there's that. Then another one is so that like scale matters a bunch. And then another one is if you're shooting tons of electrons in, so that like imagine like bouncy balls being thrown in. Imagine these bouncy balls. So you have you have a big concrete block. So like Hoover Dam. Imagine Hoover Dam was like Swiss cheese. Was just a whole bunch of little holes, a whole bunch of holes in it that were like I don't know, 10 to 20 feet wide. And just like so, all these Swiss cheese holes in Hoover Dam, and you have a machine gun that shoots bouncy balls that never stop bouncing. You have a machine gun of flubber that never stops bouncing. Um, so you shoot it at Hoover Dam, and you're counting how many get through, how quickly they get through, and stuff like that. So you shoot them in. As you shoot them in, they start bouncing around and stuff like that, and some start coming out. Um, so let's say you turn it on and off. So you turn on and off the machine gun or the electron gun. So you start shooting, and you're shooting and shooting and shooting, and the balls are bouncing around, and then they start coming out. And then you turn off the machine gun, and then you turn it back on, and you see balls start coming out before any balls actually get to the wall or the dam. And you're like, oh, this is a miracle, something weird is happening. And the weird thing is, you just messed up your experiment. You have some residuals from your last cycle. That like you shot, and the bouncy balls are bouncing around, and you didn't wait for all the bouncy balls to get out before before you started up again. So there's that. The other one is let's say and then the other one is let's say you put a certain instead of having just like as many bouncy balls as possible coming out of the machine gun, let's say you have a controlled amount. So like you have like one per second or something like that. So it's like it's on a rhythm, and it's controlled a certain amount that you can track, and then all you do is you track how many go in and how many come out on the far side, or maybe from all directions. But for now, let's just say that you're only tracking the ones that come out exactly opposite the gun. And so you're shooting one in, one in, one in, one in, one in, and then let's say like 5 minutes later, one pops out, and then another 5 minutes later, another one pops out. Another 5 minutes later, another one pops out, and it seems to have a pretty consistent pattern. But every so often, one flies out that doesn't make sense. And so you're like, well, why is there this one and why is there that one? But what you weren't keeping track of is over time, with enough bouncy balls, yes, a pattern will emerge. There will be some regularity and things like that. First of all, if you make us any changes whatsoever to the angle you're pointing the gun, or the speed you're shooting the balls at, or the mass of the balls, um, or the bounciness of the balls, um, or the shape of the Swiss cheese. Um, Swiss cheese isn't the best example, but we'll I don't know. We'll get to that in a bit. Um, if you change anything, then um, the the regularity will probably shift a bit and stuff. But what you haven't been tracking it, the balls have been bouncing in lots of directions and stuff. Um, and there's balls bouncing out off to the right and off to the left and things like that. If you go to the edge of a house and watch the drips that come off the roof, yeah, like things will form into patterns, and you might be able to track a single drop um, consistently for years, maybe if it's in the right conditions and stuff. I mean, like you go underground in caves and stuff, and things line up, and there's stalactites that are dripping at the same rate with the same quantity and all that stuff for hundreds or thousands or millions of years. Um, I got hiccups, but if anything changes, then the whole thing can get very off put. Um, yeah. So just kind of remember that for now. Keep it in the back of your head. Oh man, hiccups. So you have all this stuff. Um, with um, um, what's next? Irregularity. Okay. The other one is so matter is different than Swiss. Allegorically, uh, matter with protons and electrons and neutrons, nucleuses, etc., is different than um, like a concrete block of Swiss ch- Swiss cheese block of concrete and bouncy balls, because matter has the bouncy balls in it, and it's made up of it, and the bouncy balls are all bouncing around, and the walls are moving. So with the concrete example, the concrete seems very distinct and it's different than the bouncy balls, and the concrete holds still. That you can find a path, and so it's like almost like a game of pool. You can make your shot, and it can go through, and as long as things stay pretty consistent, temperature and pressure and wind and like consistency, like as long as the walls don't get wet and things things like that, that the ball will go through on the same route almost every time. But now imagine that the walls are made of like jello, and so like you hit it, and then the whole structure starts shaking and stuff. Um, yeah. Except so let's move back. So we're getting too far down the rabbit hole of the analogies. Let's get to the actual thing. Um, so the actual thing, um, you have it's a, like basic like I don't know what it is these days, but like I don't know kindergarten like you learn like you got the nucleus down in the middle, uh, with lots of heavy stuff in the middle, and it's not connected because of heavy, but yeah, okay. You got a lot of really heavy dense stuff, and the heavy doesn't matter for gravity, but it matters for mass. And then you have electrons that are super, super lightweight out on the outside. The electrons are repelled by themselves. The protons are repelled by themselves. So protons are pushed away from protons and pull in electrons. Electrons pull towards protons and repel other electrons. Um, Electrons are super, super light. Like, so, what was it? I want to say 10 to 30 second or something like that. That, if you look at the, if you look at the difference between, like, a pea, and the planet Earth, like, a proton is, so I say, if you were to say that an electron was a pea and the Earth was a proton, protons would be bigger than that and electrons would be smaller than that. Like, that difference still doesn't count. I think. I might be wrong. Wait. No. It's, I don't know. I can't keep track. But like electrons are tiny and way like next to nothing. Um, like literally next to nothing. Um, so the thing is, if you think of like dust or sand, so if you think of like gravel, or boulders, if you've got boulders on the road and you sneeze, the boulders don't really do anything; they just sit there. Um, if you take like a leaf blower or an air compressor and you shoot it at some gravel, the gravel might shift a bit and even move a few feet. Um, if you um, oh, if you sneeze or even just like move your hand through the air, um, near some really fine particulate dust, um, then all of that dust instantly goes like flying everywhere type stuff. It fills the room and just like even just the little tiny push, even the little tiny movements of just the air alone can keep dust aloft for like, I don't know, maybe not hours, but like up to an hour maybe in like a pretty still room. Um, yeah, so electrons are kind of like dust. The tiniest little movement makes them go flying, and by flying, it's like near speed of light speed. Um, so like you do anything like you you take your finger out and go as slow as you possibly can, and you touch the desk in front of you or the chair or whatever. Um, just simply doing that has caused electrons to go flying like crazy. They were already flying like crazy, but that caused them to fly like crazy a little more, at least for a little bit. So like the least little thing will make them go flying like crazy. Um, it'll make protons go like shaking around like crazy too. Um, but because electrons are so much so much lighter than protons, electrons will take the most of it. Okay, not quite accurate. Electrons will proportionally look like have a much more visible reaction. I guess that's a better way of saying it. Kind of like if you take a tennis ball and you put it on top of a basketball and you drop them together, the basketball, um, and then when they bounce, the basketball will bounce a little bit and the electron will go flying really far. Um, as far as those mechanics, I'd have to think about that for a little sec. But basically, yeah, the electrons will go flying like crazy. Um, and Yeah, the electrons will go flying, and then the electrons reaction will will interfere, will mess with the protons a bit, but the electrons will take the brunt of it. Yeah, because of proximity and because they're just so much lighter. Um, the I gotta get going. Um, with quantum teleportation, um, you shoot an electron at matter, which is basically a bunch of electrons flying around a bunch of protons. You shoot one more electron in there. The electron, first of all, is just going to join in with the rest of them. If you shoot it fast enough and things like that, the electron might just blast its way through. But when it blasts its way through, it's probably going to cause a little bit of disturbance for a few other things. It's going to push the protons around. It's going to push the electrons around. Electrons are probably going to fly off too, and things like that. Um, yeah. But you shoot the electron through. Boy, and it interferes with other electrons and things like that, and the other electrons get shoved around and stuff. Maybe the electron you shoot in joins up in one place and then causes kind of a like a wrench in the works almost. So like if you imagine like an old style uh, like a waltz or something like that, like a big dancing group, and they're all dancing in partner and stuff like that, and everybody has a proper place. And then imagine one person just randomly comes in and like just tries to join in, and so suddenly you have one group where it's two guys and one girl, and then when you go to do the bridge thing, like you're uneven and all these things, and so something weird happens, and let's say that the one person joining in um, causes so let's say when you go to join up, you every guy grabs a girl and every girl grabs a guy, and there's one left, and so you like one guy pops in and then another guy ends up popping out, at least for here and there a second or two, until the one guy finds another partner and stuff like that. And so by having an uneven amount, you have all these little disconnects and stuff. Um, Either one more or one less and things like that. And then let's say you start shooting more electrons in, and then the electrons start joining in, and it's like you'd be adding a lot of guys, and then suddenly like all the guys don't know what to do, and they're all getting confused, and the girls are getting confused and stuff like that. Or you add girls and stuff, and it's a little bit different with electrons because it's not guys and girls, but everything has its place type thing. It'd be like a business, like let's say like you work at any place, even something like as mundane as McDonald's or something. Let's say you've got like a guy working on the fryers, a guy working the headset, a guy um, doing like some cleaning, like cleaning the bathrooms, and another guy doing this and stuff like that. And then you throw in another one, um, and maybe the guy knows how to do everything. That like maybe everybody knows how to do everything, but they don't know which thing they're doing, and they're thrown in, and then like one guy goes in and starts helping cleaning the bathrooms, and then the guy cleaning the bathrooms is confused. He's like, "Well, wait, where'd you come from?" and like stuff, and then he goes and talks to the guy on the headset, and then the guy on the headset's confused, and he tries to call the manager's like, "Who is this guy? Like, is he supposed to be here?" And then another guy shows up, and he starts working the headset, and then you got two people talking on the headset, and just yeah. So like everybody might be the same. Everybody might be able to do everything, but um, that like things kind of settle down and stabilize into a system that seems orderly and functionable. But by throwing in extras, there's like an adjustment period where you have to like refigure things out, and so that's what happens with when you like add electrons or remove electrons, or protons or almost anything. Like you add something to the mix and it changes things. That's what happens with reactions. Like gasoline goes stuff like that. Yeah. No, no, no. For me, it kind of helps me keep moving. Oh yeah. But like I don't know, but I get you never like you start studying or something, and then like half an hour later, you're like, wait a second, I'm just watching YouTube now. Or, oh yeah, all the time. Yeah, yeah, but like, yeah, I don't know. It just, I don't know. That's awesome. Okay. Yeah, I don't know. Thanks. Sorry. No. Okay. The what next? Oh yeah, yeah. Okay, so things get disrupted and interrupted and stuff like that. There's an adjustment period and things. And then the other thing is, so you throw in an electron, um, and it joins in, um, and starts interacting, and then pretty soon, you keep adding electrons, and then all the atoms near the middle of the mass, um, are trying to restructure and reorganize and rebalance and stuff. And so like, so this atom likes, or this atom balances well with 4 electrons, and this atom balances well with 16 electrons, and this atom balances well with 5, and so on and so forth. Um, and this combination of atoms balances well with this, and so on, and all this stuff. So they start balancing out, and then in order to balance, they have to like just kind of let the electrons fly away. And it's not like in a agreement and stuff like that. It's usually just like electrons grab on wherever they can, and once a handhold is taken, then there's nothing else to grab onto, and they kind of just go flying off. And it's not a handhold and stuff like that, but it's a balance of, yeah. We can go through the exact dynamics and stuff, but allegorically and stuff, there's no handholds, and they go flying. They they're off the boat, whatever. Um, and they go flying, and they go find another one, and then they then by joining another one, they unbalance that one, and then that one, another electron goes flying off, another electron goes flying off, and pretty soon the entire surface of this material is all losing electrons because, you have so many extra electrons that there's no place for them to grab, and so you're like displacing electrons. You're pouring water into a full cup. So like you got a cup that's full already, or a bowl that's full. You start pouring more water in. There's no place for the water to go, and so you start displacing it. And so some of the water that was in there first might get dumped out, and some of the water that you're shooting in might dump out as well, and stuff like that. Um, yeah. So you're displacing electrons. And so when you're displacing electrons, electrons are flying off in all directions and stuff like that. And then so let's say that, um, um, you shoot electrons in, and you start saturating. So it's like a sponge, that you're adding water to a sponge, um, and the sponge takes a while to soak up, and then eventually it'll start just like dripping water out of every pore everywhere. If you have enough pressure, like if you take a hose and you shove it up against a sponge, eventually water will start, coming out everywhere. Alrighty. Yeah. And so when you have it fully saturated and at a consistent rate and all that stuff, um, you're putting water in, and a very consistent amount comes out. Uh, and then as long as you're above a certain saturation point, you crank up the water that you're putting in, and you have a very, direct, not immediate, but close to immediate, reaction. So like you saturate the sponge, water's coming out everywhere on the sponge. You turn up the water, and more water very soon starts coming out of the sponge. You turn down the water, less water comes out of the sponge.
But if you get below saturation point and you start having gaps and stuff in the sponge to where the sponge doesn't have water saturating certain parts of it, then you have holes, and those holes create, I say it, those holes um, create gaps. So you start slowing down, and then holes start creating, and so um, the water coming out of the sponge can actually slow down faster than you turn it down. So like you turn the water pressure down, um, and suddenly the sponge actually starts soaking up water. So the water that was going out of the sponge actually starts getting sucked back in and stuff like that. Um, and then let's say that the sponge starts to dry out because you're filling it slower than saturation, or you're filling it below saturation. Um, and so the sponge isn't filling up. And then when you turn the water pressure back up, it takes a second for the sponge to actually saturate and go, type thing. An easier example would be like a cup or something where you can see it all, and it's like only it's not a sponge with like multitudes of cavities. It's yeah. If you have a cup or a bowl, and let's say you start filling a bowl, um, water won't start pouring out of the bowl until you actually fill it. So if the bowl is empty and you start filling it, it might take 10, 20, 30 seconds before the water gets to the top, and then the water start pouring out. And so you turn on the faucet, and if you're tracking water coming out of the bowl, nothing happens for 30 seconds, and then suddenly a lot of stuff starts happening. You turn off the water, and the bowl's still full. You turn back on the water, and water instantly comes out. You dump the bowl again, and it takes another 30 seconds and stuff. Or let's say that you tip out half the water, and then you put it in, and stuff like that. So just you have the whole saturation thing with the electron gun and quantum teleportation, and so you'd have to somehow balance that out. Um, and so there's that. The thing is that, yeah. The other one is the Swiss cheese thing. That it's Swiss cheese that you could get a very very lined up thing, and so instead of Swiss cheese, it'd be more like a structured um, thing. And so all the pathways would be predictable and stuff. But you have to try really, really hard to get it a completely crystalline form. I want to say they do a lot of quantum stuff with crystals and things, and so maybe they do. But yeah, um, boy, either way, it's yeah. So there's that. Um, I need to get going. The other one is okay. Then the other one is uh, uh, just interactions at a distance, and so um, electrons repel other electrons like magnets. That when you put two sides of the same sides of a magnet together, so two magnets with two norths together or two souths together, um, they repel each other. And so electrons repel other electrons without having to actually touch them. And it's it's really really strong close up, and it diminishes the farther away you get, but they still have a really really long reach. And so like if you go and you touch the table or the floor or something like that, you can like it looks like you're getting really close to the table or things like that. But um, your fingers never go into the table. Um, like you go and you touch the table, and you don't see parts of the table floating around in your skin. You don't see parts of your skin floating around inside the table. Um, so it looks like we're getting really close, but we're actually really far away to the side of electron. Um, I think. Uh, Proportional to the size of electrons, definitely, and protons. Yeah. Um, that so like if we were talking about solar systems, um, if one solar system, so like we've got a planet, we've got a sun with planets around it. If another, and let's say that the planets, instead of being attracted to each other, so in gravitic systems, I feel like predominantly gravitic systems like solar systems, um, like everything is attracted to each other. So it doesn't exactly work. But let's say that the sun attracts planets, so that like planets are attracted to the sun, but the planets repel each other, and so the planets don't like to be near each other. And then you have another solar system come by with planets flying around it that repel each other and repel the planets from the other solar system, and they bump into each other. That the planets would start shoving against each other, and the suns would start shoving against each other, and they would bounce away. Um, yeah, there's so many things to talk about. So there's that. I gotta go. I gotta go. The yeah, okay, distance. So you shoot electrons in. Um, I'm trying to think. So imagine you have magnets, magnetic marbles, but imagine instead of them being plus and minus or north and south, they're only one. So you have marbles and you throw them out in a big bowl. So like you have a big bowl that like one of those big mixing bowls, like industrial size mixing bowls. It's like say this is like 4 feet across this bowl. You throw you start rolling these marbles in that are only plus or only minus uh, magnetic. Um, say that you only throw in negative ones. So they're all repelled by each other. Um, they start to so like one rolls in and stays in the center. Another one rolls in and pushes the other one off balance, and so they're pushing against each other, and so neither one of them is in the center. They're like just on the edge of the center. You roll another one in, and so you got three in a triangle around the center, and then you roll another one in, and maybe that makes four. You roll another one in, and then that makes five, and then eventually, like you make like a ring, and then eventually they break up, and so like it maybe at like 7 or 10 or 20, they had a ring that where they're all equidistant, and then some of them fall down, and so you have a ring within a ring, and then you have another ring and another ring and another ring and stuff. Um, and things like that. What was I gonna say? What? Okay, let's say this. So you have all those stabilized rings, and let's say in the middle you have a ring of, say, 8 or something like that. That ring is actually not the most stable. That more stable than that would be like 6 or 4 or 3. Would that like 3? Yeah, 3 would probably be the most stable of a center. Um, let's say like before you were adding them gently um, around the outside. Um, but let's say with this last one, instead of adding it gently, you flick it and shoot it as fast as you possibly can into the bowl, and it starts pushing all kinds of other marbles, other magnet marbles away, um, and causing them to go flying all over the place. And then they have to go and find new spaces to go. Um, and so now, instead of having a structure that instead of having one kind of structure, now all the marbles have to rearrange and reorganize and make a new structure. And it might be the same, it might be different, but in the meantime, they're all flying around and changing and stuff like that. And some marbles might get flicked out of the bowl. Some marbles might end up in very different locations than they were, and all kinds of stuff. Yeah. Um, so you have stuff like that. So you have this interaction at a distance. So just the repulsion is one thing. Um, the other one is that when electrons, so okay, this part I don't understand, and I think a lot of people don't actually understand. I maybe it's in the Lorentz equations and stuff like that, but I don't know. Um, but so basically, when electrons move in a straight line, they make a tornado. Um, so if you start shooting electrons forward in front of you, they'll make a tornado that twists. Um, so that if you were to take your hand and wrap and put your line your thumb up with the direction of the electrons moving, and then wrap your hand around the wire or whatever the electrons are traveling in, um, then your fingers would be. I think it's with your right hand. If you take your right hand and um, put your thumb in the direction the electrons are moving. Actually, it might be the other way around because they mixed up plus and minus and stuff like that. But yeah, so you take your right hand, you put it out, you wrap the fingers around the wire, and you point your thumb the direction of the wire, and it's either plus or minus. You got to point your thumb towards the plus side or the minus side, whichever one it is. Um, that your fingers show the tornado that is being made of field lines, and that tornado is magnetic force. Um, so it's not pushing away and it's not pulling in. It's making a torsion, a torque. Um, and so if you have electrons or things around in the surrounding area, they'll get shoved around by that tornado. Oh, in conjunction, if you have a tornado of magnetism, um, then a magnetic tornado can cause electrons to move in straight lines. Um, it's like I don't know. It's a relationship. Um, Theoretically, the same thing should work for protons, although it would be much more difficult. Um, that protons are just so much heavier and they're harder to move and all kinds of stuff like that. But yeah. Um, so um, let's say you have a thin sheet of metal about the size of a playing card. So you have a playing card. So let's say you have a credit card that's made out of metal, um, and you got it, and you're shooting electrons at it and stuff. It'll interact with the electrons that are being shot at it, or it'll change because the electrons being shot at it, and things will change. But you could even take the electron beam and move it off to the side so that you're just shooting them past it, and none of the electrons are actually like going into the piece of metal. Just by shooting it past it, you're creating fields that are interacting with the electrons in or with the metal, with the protons and electrons. Um, yeah, so there's so much interference, so much stuff going on that it seems really unlikely that any of the stuff that they say with all this quantum stuff is entirely um, in unquestionable. What's the unimpeachable? Yeah, I want to say infeasible, but that's not the right word. Yeah. Okay. Um, yeah, what else? There's yeah, let's stop there.